the thing is that, yeah, I mean, let's see how it goes actually. Okay, so I'll be talking about something which is actually, I mean, it's a bit technical in the sense that I think so, I mean, it is an asymptotic symmetry algebra actually. Okay, so I'll be just using some of the EA in the sense that, I mean, this is about this holographic EA came from the spatial holography, and let me first write down this thing. So just few brief review about what this thing is. That so in celestial holography, that what we do is that we write the scattering amplitudes as correlation functions. Which lives on the celestial sphere, and celestial sphere is this. It's a cross section of the slide of the spirometer. It doesn't matter what you take. You can take all the particles to be outgoing, and they just go there. Okay, and I'm taking. Well, I mean, you can do it for both massive and massless case, but I'm just talking about the massless case. So that all of them reach actually strike plus.
And Shamik, the CFT is a Euclidean.
Yeah, yeah, it's an Euclidean CFT actually. I mean, because the point is that it lives on its base too.
In EDS CFT, we have this notion that boundary time evolution and bulk time evolution are tied together.
Yeah, here actually it's a null. The time, I mean, the time evolution, if you think it's in the null direction. We can also talk about that, but the thing is that, I mean, the reason that it naturally, well, I mean, I'll just explain that why it becomes a two-dimensional game, in the sense that, so the when I'm writing the scattering amplitude, so it's a function of the P mean, so let's say for the massless, it is 0, so I have three independent quantities, which is like you can take it to the energy, so you can write your E, some E. And so this, if you write this, then this will automatically hold. And n is a unit vector, n dot n is 1. It's a spatial vector, and the point is that when I'm going to the celestial sphere, what we do is that we do something, say phi. It's a bar,
Can't I think of the celestial sphere as spatial infinity, that where the two intersect, and then and then you add the generator to go up and down in the algebra.
Spatial infinity.
I mean, that what do you call it? You go
I0.
I0. I mean I0.
Yeah.
I can't think like that.
Well, the spatial infinity is just one point, so you can.
I mean, a sphere
resolve that.
You go off to infinity in all directions, and the direction is the
Well, so in this case, when I am talking about the massless scattering amplitude, I mean they are not going to this point.
No, they're not going there.
Yeah, but you could actually bring it all the down. Yeah, I mean it is, in a sense, it is defined in that way. Only like this thing actually moves. I mean when I do the law of Lorentz transformation, so this cross section will move and you can bring it here also. So that, so where it is exactly located, that itself is not an issue.
Is the sphere, and then the algebra either includes moving in the time direction, which is for ADS, or in the null direction. As
Yeah,
so it's not like that.
Well, I mean that there is a time direction, okay, which is this null time. Okay, you could also move in that area. So that is called, sometimes called this Gaussian area. Now the thing is that now when you come from this scattering amplitude side, actually, I mean I just explained that. I mean why? So then you need something which is a function of say z bar and e. You need basically three-dimensional fields, but you don't have those many degrees of freedom actually. Because this, okay, I mean, let me just write this thing and then I will actually use not this one, but rather. Okay, so Z and Z bar, they are complex number which are complex conjugate, and this omega is a real number which is very zero. And the point is that the way we define this thing is that I have E epsilon omega bar sigma is the helicity. Now the thing is that you can see that this A is the creation and integration operator. And that depends only on the energy and the Z bar. So the way it is done, you integrate out the energy and then that is replaced by this delta is some number. It is the weight, I mean, which will turn out to be the weight. So this H is actually just delta plus sigma by 2. H bar is delta minus sigma by 2. Okay, and then this phi is automatically becomes two-dimensional field. So that's why, but you can actually introduce this U. In fact, I mean, we have done that. But yeah, I mean, for what I will do, it does not.
Roughly the Z and Z bar are the direction.
Directions, yes. So the thing is that, yeah, so let me actually draw this thing. So Z bar, they are actually stereographic coordinates. So this is the Z bar, and this you can call it E. So this is the two-dimensional sphere. I mean, it's a cross section. It's not. I mean, I have drawn it in this way, but it moves. I mean, once you do the law of the transformation, because the way is U will transform. So U just goes. If you do law. So and CD it is just an eccentricity transformation because SO3 chromosomes. So you can move the sphere. So if you look at a fixed tube and then you move.
Can you say a bit more about the parameterization of P mu? So earlier you wrote subtract the P.
Yeah, and it is just going. So this is actually these coordinates. So that makes these fields these ZZ bar. These are actually stereographic coordinates. So you can think of them as living on the plane. Now, if you write this in terms of E1, n hat, where this n hat is a unit vector, then it becomes a field on the sphere. So you get some additional factors of this square root G which comes.
Yeah, so for this n hat, if it is written in ZZ bar, then ZZ bar is like the direction, but here even the energy is omega times 1.
Yeah, I mean, so E is just your omega times 1 plus ZZ bar.
So ZZ bar is still thought to be as the direction on which.
Yeah, I mean ZZ part is still actually thought to be as a direction, because these are the so this n hat. So this n hat actually, the components of n hat, they can be written in terms of this ZZ part. So this is essentially. And this n hat is the asymptotic direction in which these massless particles move after the scattering takes place. Okay. So these are later on the free particles.
Is there some natural interpretation for the ADM and the CFT?
Well, the notion of a Hamiltonian, well, I mean, that's a bit tricky actually. No one really has I mean, that is better done actually once you have this movement in this.
What did you have in mind, Luca?
I was just
ADM
trying to
energy.
make some connection to the way you think about an ADS, right? There we have an ADM energy which is the same as which is identified as the boundary Hamiltonian by the
Yeah, but here actually the Hamiltonian of the CFT, well, you can talk about the energy, well, I mean the energy, of course, is being integrated over here. So that information somehow goes into this scaling dimension.
The boundary theory seems like a Euclidean two-dimensional theory where
Yeah, it's a Euclidean two-dimensional theory, and it is not necessarily an analytic continuation from a theory. So it is some. I mean, if it is true, then it has to be an intrinsic. I mean, it could be an intrinsically Euclidean. So the notion of unitarity is not necessarily that you get from the analytic continuation. Okay, so those things are.
For example, does it preserve reflection positivity and so the Euclidean theory? I mean, since
I
you brought up
mean, it doesn't have to be. The only thing it has to make sure is that this bulk unitarity somehow is preserved. And the thing is that the bulk unitarity requires this delta to be like in 4 dimensions. This actually requires this to be of this form, where lambda is unique. So this is this unitary principle sequencing.
So, Omkar's question, there were all these charges that were defined
On the
basically on the space-like surface, right? So
yeah, I mean,
area and
there is a
everything.
stress test there.
You know, as you guys know well, I mean, there is this holomorphic function that you integrate over the stress tensor.
okay.
And that, from the space-time point of view, was defined as on scri plus, but in the limit of
Okay.
negative infinite time. So essentially on the space-like surface, right?
Yeah.
And one of them must be ADM energy.
Yeah, but it is integrated on the whole sphere.
Yeah.
From the CFT point of view.
From the
it's not a very
CFT point of view,
it's not
the charge.
It's not the Hamiltonian, no.
Yeah, I mean it's not. So I'm saying that I mean it's not necessarily that actually.
Oh, so that's what you want. You wanted whether ADM energy was generating time.
Right.
Okay.
Yeah, because the thing is that the notion of time evolution in the context of S matrix is well, I mean it is already the time is well, I mean things coming from infinity. Yeah.
There is two CFT. I mean, there is two four-dimensional surface on which the CFT is.
No. I mean what I am actually assuming is that like all particles are outgoing. Okay, so I have an index here which is epsilon, which tells me. So you can think all of them as sitting here.
Okay. Sorry, I just follow up again. Suppose we got to flat space limit from ADS. Forget about the S5 and so on. Then what is ADM energy in flat space is basically the ADM energy on in n equals form. So in that context, that really plays the role of evolving initial data to final data.
Yeah.
So somehow, if we take that analogy, it's like these 2 bits of data that should be roughly evolved by something like that ADM energy.
Yeah.
At least in the ADS context, that happened.
Right.
Whereas here, it's more like you're separating out, right? This little wedge here, this little wedge here, you know what I mean? And ignoring the evolution between.
Sorry, I did that.
Sorry, let me say again. One way of thinking how flat space, I should be talking about, well, shut up. But one way of thinking about how flat space emerges out of ADS is this, that you look at, you take the limit ADS, radius goes to infinity, while fixing on, working in a small band around global time pi or minus pi. So then we take this little band of the CFD, and the other little band, the past band and the future band, and you ignore everything in the middle. So you look at these correlation functions that with operators inserted here and operators inserted there. You take the appropriate level and you get flat space correlations. Okay, you get the S matrix and so on. Okay, but all of flat space comes from this little band here and this little band here, ignoring the stuff in the middle.
You're ignoring that.
So the evolution part is somehow thrown away.
It's thrown away, exactly.
Also, the time evolution is already taken care of in the sense that I mean that's what you get by you just look at what is happening in the far past. I mean that's what he's saying in these bands.
So in that sense, the full space-time in the bulk in flat space is just dual to two states or something like that.
Well, the thing is that I mean
Correlators, that's true. You have to look at correlators in this region. But if you wanted to know if you had correlators here and you wanted to find what they would be there, you need the Hamilton.
Yeah,
but
and
within those bands, there's some notion of time evolution using the Hamiltonian, right?
Yeah.
Where is that?
That will be essentially like free evolution on the boundary.
because these are all free. I mean, after scattering takes place,
Nothing happens at such
just
a
like this thing, something happens here, but we don't know actually. I mean, we are not able to see this. I mean, we just want to see what is happening after the interaction.
So, as you know, Pratik, one of the great things about flat space is that early times nothing happens, and late times nothing happens. It all happens in the middle, right? So that early times nothing happening is some trivialized thing.
No, but the energy has to be conserved starting from.
Yeah, so that is there.
right?
No, so that thing is there. Yeah, I mean that I will come actually. No, so all those things are there. But this Hamiltonian, well, I mean, if there is a stress tensor, it could define an L0 bar and from this thing. Yeah, but that.
So I suppose what I'm saying is that what you need, the main role of the Hamiltonian scattering is relating past to future data.
And it is already taken care of here.
Yeah, here somehow you write one field theory this way or one field theory this way, right? The evolution is just through conservation laws, that's just, I mean, constrained by conservation.
And those are all contained here. I mean, I will come to that actually.
But in this Carolean description, there it's like sphere as a function of time or something, right?
Yeah, I mean there you can talk about the, well, I mean the thing is that I mean you can write down this space. So what you can do is that instead of doing this, I mean you can add this factor. Okay, in this thing, and then it makes it a function of u also. But it's a bit, well, and then actually you can show that these are actually fields which live on the three-dimensional scribe class. And that transforms exactly in the way you want.
And then there
but
is some map from
evolution is not exactly the Hamiltonian. Well, I mean, I don't think that. I mean, this is a more formal way of constructing these fields on scribe class. But these things that things move here and then the Hamiltonian generate. I don't think.
But this is also again on scribe class.
It's on scribe class.
Evolution on scribe class, and there's a separate evolution of scribe minus. And S matrix is taking what happens in scribe minus to scribe class. Even that, this doesn't attend that.
You can
but
write
just
this-
on scribe plus itself, is it like just there's some notion of time evolution along scribe plus or that?
Yeah, I mean you can write down these fields, you can transform your expressions, but that is not exactly what is actually asking. Because I mean, but these conservation laws which he's asking, I mean those are very much part of this actually. I mean that's what the aim is. Okay.
Sir, one more question. So, how do you define the boundary here? I mean, the boundary can go under non-evolution or the time evolution of the boundary. So,
Well, so the boundary here is that, I mean, those are all the directions on which these things actually go. So these are finally determined by two things. So one is the energy and the other one is the direction in which it moves actually. It's a set of all n hats, which is an XP. That's how you can learn.
I'm so sorry. What was the upshot of the definition of energy? I thought what you were saying here in this formula is omega was the energy.
Omega
into 1 plus I.
Yeah.
But because of the convolution, that information gets
Now that
HH bar.
information goes into the scaling dimension.
And so you
So now actually you get a function, you get a field which are actually, if you don't have this,
yeah, you don't have this. in your
suppose you don't have these things, then it's a function of z and z bar, so it's a two-dimensional field.
Is it true?
It's not a three-dimensional
is not discrete, and HH bar. If you
HH bar, of course, is a fixed once and for all. I mean, in
no,
the
but
sense that-
for every bulk field, don't you get many, maybe infinite number of deltas or something?
Yeah, so the thing is that when you do the inversion, you have to integrate.
Integrate over.
Yeah.
So the
Over
information
delta.
of energy is in that.
Yeah, in fact, the point is that
inverse.
this delta is equal to 1 plus I lambda, lambda is continuous.
And through some involution or whatever, the information of energy is in that.
Yeah, yeah, I mean, it is here. How, I
That's the way
mean, yes.
Okay.
This is how actually you get. And the fact is that this lambda is actually continuous. So delta is not a fixed number. I mean, unlike usual conventional CFTs. But then there are many questions. I mean, the main question is that whether these are, I mean, then, because these are more like, well, I mean, whether these, I mean, the main question is that if there is a state operator correspondence or not. Okay, so it looks like that may not be there. Okay, and then the thing is that I mean all of these deltas, I mean with all 1 plus I lambda for all the result of lambda, they are not necessarily operators in the theory. So it is more like a usual field theory. So you have both normalizable and non-normalizable states. And then, I mean, so it is a big, yeah, actually, so, but that part of the story is still it's the work in progress. But the point is that I will focus on a set of deltas which actually don't fall on this line, this 1 plus I lambda, and those are actually discrete and integers. I mean, those are actually all well behaved here, and those will turn out to be the most powerful thing actually in this thing. Yeah.
The fact that S matrix is unitary,
Hmm.
can that be written in terms of CFT formulas?
Yeah, I mean the thing is that I mean that is people have done that. I mean like, but I don't exactly know what is the status of that actually. I mean,
But
well,
so can we
so the thing
compose-
is that the unitarity of course is not lost because I am doing an inverted transformation. But how is it from purely from an intrinsic CFT point of view? So people have actually, well, I mean there are only very few.
So does that then become a consistent structure, two-dimensional structure also that we can see?
Yeah, it looks like actually. I mean, what do you mean by consistent structure in the sense that?
You can try to solve for it. Maybe in the secret you will just be.
Yeah, no, we can actually solve. I mean, we can actually solve. In fact, the point is that this compilation function. So let me just write this thing. So
the factorization limits are they in some sense effectively?
yes, yes. I mean, in fact, all of those things actually exist. So the thing is that, yeah. The only thing is that I was not planning to talk about.
That's fine. So what I'm asking is that in all the conditions you want to impose can be just imposed intrinsically on the two-dimensional structure.
Yeah, that can be done. I mean, that translation can be done. However, I will say that I think a purely intrinsic definition is still missing. I mean, once we have that, then bulk of the problem is solved.
Sorry, purely intrinsic.
I mean, purely intrinsic in the sense that I mean, a lot of these things I mean that I will do. I mean, they actually came from how this S matrix in the bulk area, and then actually that teaches us actually other things. But we have to somehow use this S matrix here. I mean, we don't know what is the exactly the dual.
The condition doesn't sound very natural formulated from this point of view, right? The unitary looks quite ugly.
Is it because you
Yeah, I mean, in fact, the thing is that I mean, no one has done that.
insertions
I mean, and that essentially, I mean, after so long, it has not been done. That means, I mean, that's a very fundamental thing. I mean, it is not just some.
Well, for our quantity, we did it in that way.
Yeah.
For the quantity that is not exactly your quantity, whereas the
Yeah.
level transform.
I'm already sorry, Shiraz. Relating the in going to that
Just look at action as a function of boundary.
Okay, in this case, I
Okay, look at action as a function of boundary.
so these kind of
Constraint is unitary.
correlation functions are there.
But did you relate it to the data at scribe plus and scribe minus?
Shamik did. Shamik did.
So these actually what Siras, Onka actually they got. So that is actually okay. So let me write this thing actually. So this phi. So these are the correlation functions of. So this is essentially.
Can you say it again? What is it, epsilon later?
Yeah, I have not said it yet actually. So for epsilon plus 1, it is outgoing, and minus 1 is incoming. Okay. So this is actually this. Times S, which is a function of omega of all the variables actually. R and sigma. So this is the S matrix, and this is how we actually get.
But the incoming and outgoing in the
Yeah, sorry. So this, yeah, sorry. So this is actually epsilon I pi. Okay.
Correct.
So pi is this. So it is the sign of the energy which will give you.
Yeah, that's what I was thinking.
Okay. So this and sigma is the helicity. Okay, and the quantity we actually see as Onkar they got actually. So you get this thing, and you can do a shadow transformation of this. Then that actually gives you those quantities which are. Because at low point, for example, if you compute the 4 point, this 2 to 2 scattering, then if you just do this, you get a, something like you take of z minus z bar, where z is the cross ratio of the 4 points on the scale. But then once you do the shadow transformations, those things are gone and you get a nice answer. Okay. So that is how it is actually related. In fact, the shadow transformation, not just there, it actually, in fact, if you want to construct a stress tensor, also there actually you have to do a shadow transformation, and most likely it is related to the fact that we are still not sure what is the source and what is the A actually. So what we are talking about, these things are most likely sources. So when you go to the A, you have to do this non-local transformation. Now that's a very interesting thing which has not been fleshed out yet because they stopped. You guys should take off. No, I mean that's a very important point actually. I mean that why this transformation. I mean this. What is the source and what is the what is the boundary here actually? Because ideally, I mean these look like these are like the sources. I mean they are not exactly. But anyway, so this is the thing. So
the state, not the source, roughly something.
Yeah, so that is, so this phi's, I mean, you have this phi's here, which are, so that is like the source in the DSCFT, and then you do the shadow transformation. Yeah.
What is the ingoing and outgoing?
Huh?
Ingoing and outgoing, what is it?
Oh, ingoing means, I mean, so this is just an S matrix. So there is some, say some two particles scattered. This is like these are the two incoming. These are the, but now actually I am writing this as this. All outgoing, but then you have an epsilon here, which will, I mean, 2 epsilons will be plus 1 and 2 epsilon will be my cancel. Or, I mean, usually we say that the sign of the energy, depending on that.
So these epsilons are basically this identifies the CFT amount, not the non-test.
No, I mean, it is not the, well, I mean, these, you can think of this as the bulk here. So this is, I mean, depending on the sign of epsilon. So if epsilon is plus 1, this is A, and if epsilon is minus 1, this is actually A dash. Okay? So that's what I mean. So that epsilon actually goes here, which is which operator, which one is incoming and outgoing. Okay, so this is actually how it looks like, and this transforms, I mean, it is very easy to see that this will transform like an endpoint function of a CF2, I mean, under the global conformal transformation, which is the Lorentz transformation in this case. Okay, so now the thing is that the currents. I mean, these are the most important things. I mean, most important things in the sense that I mean, lot of things actually are known about that, and they turn out to be one of the most important things here, which is actually how do you define these or these currents. Okay, so they turn out to be the soft operators. By soft means I mean the standard soft limit. So suppose I compute, say, suppose you have some scattering amplitude in QED. Okay, so things just, and then you have something go out, and then suppose it emits, and with one outgoing photon. And then the point is that, say, which has some energy momentum Q, and the soft means that you take Q equal to 0. Okay. And in this limit, this S n plus 1, which is the n particle. So n, say, and n here, and this one refers to this. I mean, n is the number of all of this, and then 1 is just for the photon. So it will depend on some pi. Okay. And then you will have Q, and then as Q goes to 0, okay, so this can be written in a factorized form, which is given by sum over I and EI not 7 times your Sn times and then order. Okay. So this is called a soft theorem, which tells you that if you take this Q to 0, then this n plus 1 point S matrix will factorize in terms of an n point S matrix, and this is the contribution of the soft form. Okay, and you can see that this is the most important. Here is the charges. Okay, and from here you can see that this is gauge invariant, and the gauge invariant is just a consequence of the charge conservation. If you set epsilon Q equal to Q, then you will get sum over I EI, which is 0. Okay, so that's the charge conservation.
Epsilon of Q is the polarization.
Polarization of this photon. Okay, so the point is that you can do the same thing for a graviton also. You can do the same thing, which was done by Weinberg, and then you will see that this type of A is actually replaced by some other soft factor. But the point is that this Sn plus 1 actually factorizes in terms of some soft factor times Sn. And the basic idea, which actually works, is that this actually turns out, this has exactly the form of a word identity, which actually tells you that an n plus, you have an insertion of a soft here, and then it factorizes like this. Okay, you can define, suppose if you have this Q here, so if you in fact this Q, if you write this Q as omega times.
Can I just ask one question about this?
Yeah. You just you don't have to ask actually. You can just ask me the question.
Here you've written the soft theorem at the level of a matrix element, S matrix element. Maybe you put in some specific incoming momenta, some specific outcome. Is there a version of the soft theorem directly at the level of the S matrix thought of as an operator? You know what I mean? Like S matrix, you can think of a unitary operator taking the in Hilbert space to the out Hilbert space. So it's sort of one whole object in a sense. Is there a sort of operator statement of this operator?
Well, if it is true for any
of course.
Yes, state, in that sense it is true.
Yeah.
But
is there any sense?
Well, I understand. But that S, of course, that it's there is one S.
Yes.
Okay, that S acts on n plus 1, n plus 2, all of them.
Yeah.
So S as such it does not know about n.
Correct.
So what?
Like those are some matrix elements of that S.
Yeah, that knows
Some
about the n.
straight like this.
Yes.
So what I'm saying is that this S hat Okay, so I mean I have some out state and then
natural.
some in state question. Now this S hat, of course, does not know about this in and out range. So yeah, so I think the soft factorization has to have information about what kind of in and out
Matrix
states.
element by matrix element.
Yeah, I think it's I mean otherwise, yeah, because the thing is that I mean if you don't have an photon here, suppose all are just say some scalar charged particles, then you don't have any factorization.
It's a little like a what identity.
I mean, it is exactly like it has the
I was
formula.
wondering whether there is a statement directly at the level of S hat.
S hat. But I was thinking that S hat, if you write it in Fock space, could you make a reasonable statement?
But that's what we have done. I mean,
Yeah.
it is a
Matrix element by matrix element, I see what it is.
No, but I'm saying in Fock space, independent of what, that you've got this S hat acting on various things.
Yes.
You take one of those Q's to 0, and then it becomes S hat acting on that plus a photon.
Indeed, yeah. So
It's
that's some familiar or simple
It's
thing.
very much like a Watt identity, right? Because a Watt identity is del mu J mu, which is one extra photon on various other things, is related to things without that photon. So transforms of this. So this is very much like that, right? Because it's got an extra gauge boson on one side, and nothing on the other side, but some factors like the transformations, gauge transformations.
If you wrote the asymmetrism LSC reduction formula, it would be very close to a Watt identity, right?
Yeah, I mean, this is, I mean, this has,
replaced by
well, there is one difference which is actually, of course, the most here. So so this is actually, of course, I mean, I have some scattering happening here and then some photon insertion. So this is essentially J mu of some say Q, and then this thing, and then I am getting Q to 0. Okay, and then actually you get this factorization. Now, if I just write the usual word identity with some bunch of other fields, say, I mean, these are all 4-dimensional fields, I mean, the usual given actually, then, of course, I mean, I will have structure like some BI, we get the function, x minus xi, and then something like this, right? Now the thing is that I mean one difference. I mean this is more powerful. I mean this is more powerful than this because in most cases we can't solve for this J mu. I mean only in 2D CFTs in some cases we can solve it in terms of J mu times this. Okay. Whereas here actually it comes. I mean what we get is actually this. I mean it is more powerful in that sense.
But in some sense, if you take this integrated to the boundary.
Yeah, but the thing is that I mean, but that gives you only the global piece of data. So if you do an integral, I mean say I'm operators insertion here, I do the integral, then I get this Q acting on all of these things. I mean which gives you the, but these has a local form actually. I mean that's why it becomes much more powerful and it becomes an infinite dimensional.
Still, I think if you take the Watt identity and apply it to the bulk point singularity in ABS, I think you'll probably recover the statement.
I mean, which statement? This one?
Yeah, so let me say
Yeah, I mean, I asked you exactly the same thing.
You asked me exactly?
Yeah, that that is one thing, I mean, which one should actually do and how to.
Somebody must have done it in some way.
No one has done that.
Okay.
Do what? Sorry, do what?
Let me say.
I mean, that's a very interesting thing actually to show. I mean,
consider
it's an easy thing to show, but it's an interesting.
Consider correlation functions in ADS CFT. Okay, consider a correlation function with the J mu and matter fields and without the J mu fields. Okay. Now each of these is related to an S matrix by a bulk point singularity. Right. So we know that we take a bulk point singularity of the J and other things. We get a correlation function including a photon. S matrix including a photon, and on the other side, we
but you have to take the flat space.
Take the bulk point singularity.
Okay, I mean,
I'm just looking at the bulk point singularity.
Fine.
Okay. Now, all these correlators obey the Watt identity as an exact statement. So you take that statement, impose the fact that they have the bulk point singularity, and read off what it becomes on the residue of the bulk point singularity. What does the Watt identity become? How does it constrain the residue of the bulk point singularity? I haven't done this, but my guess is that this will turn into the software. I think it sounds very reasonable because it's a very similar structure.
Okay.
Yeah, I mean, it has to come.
It has to come.
I mean, there is no use. But the thing is that, what I'm saying is that if I look at the usual word identity in QED in the 4 dimension, which I think
I agree with you.
more in the sense that I mean, which in 2D CFT, why it is most powerful, because we can solve these things because of the analyticity. I mean, once we know these entities become some del bar of this, so we know what changing intent is, and that makes it so powerful. In fact, so these actually has already comes in a solved form. I mean, you don't have to solve it. So, and that is the most powerful common strength. So once you start thinking of them as word identities, that becomes powerful.
And the fact that Q going to 0 limit is being taken, that just means it's J.
It's J. Yeah, I mean it's J. Yeah. Okay. Yeah. I mean that is just J.
It's a conserved
Yeah.
operator.
Yeah.
It's like zero momentum, right?
Yeah. I mean these operators. So it is like your A. This is like your A equal to 0 and sigma.
So can you say again how is Q going to 0 similar to like having a J?
No, not Q equal to 0. So if you have these, so I mean these types of things, I mean it is just an insertion of the J mu Q. Okay, you can take Q going to 0, and then yeah, I mean then that's this soft theorem.
No, but you are saying that what it gives you is a correlation function of J.
Oh, no.
accepted at
So
any point.
I did not say that. I mean, this is the same thing as this one. But what I'm saying is that compared to the 4-dimensional, I mean, if you just write the word identity, I mean, just the word identity for the E1 in the QED, then well, you cannot solve this thing in the sense that I mean, this comes from this, and then you get. I mean, you don't know exactly what this object is. Okay. Whereas in these cases, if you think of them as word identities, which you can actually mention that in DCA, then actually it is basically giving you. Well, I mean, let me just write this thing, and then we will show that I mean where these things. I mean, this is a 4-dimensional thing. This J mu x. I mean, this is the bound. So this has nothing to do with this the word identity of the A, but the global part of that will match with this. But it has other local symmetry. So in that sense, actually, it is more powerful than this. Because the thing is that, of course, no, what is the?
No, sorry, I'm very glued out of.
No, just go ahead.
I mean, we, of course, what Shiraz was saying,
Yeah.
interesting, but it is more dumbly just to understand. If I just took the LSD formula,
Yeah.
wrote it in terms of correlation functions,
Right.
you know, with the amputation
Uh-huh.
procedure, and then use the word identity in the correlation functions, I should get here, right?
I mean, you have to take the soft limit.
And yeah, take the soft limit.
I mean, it is exactly that actually.
It's exactly that. Yeah.
Yes.
Okay, that's.
No, there is no error.
Sure.
But the thing is that when you interpret it as a 2-dimensional, I mean, but I will show that I think this can be interpreted in a 2-dimensional word identity form. I mean, that's the thing actually.
That's the
which-
power.
Well, I mean, once you think in along that line, you see that I mean how things work.
Sorry, but
Okay.
in 4 dimensions,
Yeah.
if you take the correlation functions and take this LSD formula, there in these correlation functions, if you want to use word entities, would have to have a J in them.
No. So all of those.
No, I mean, the
those
kind of
things
thing
are-
that Sandeep had in mind would
Yeah,
have
yeah.
a J in them. But
Right.
here, this is just a
So
photon.
it is this J
photon
actually
operator.
which I wrote actually. Yeah.
In 4 dimension, it's not quite a current, right? For which you would use the word identity. I mean, I don't know whether that's what you had in mind or something else. But
Yeah, no, you're right. I had a photon insertion.
Yeah, the photon
But
insertion
there
is
is
the
a-
J mu tilde of Q.
Yeah, I was.
no, but 4 dimension word identity. In order to use that 4 dimensional thing has to be a current in there.
I think that's Abhijit's right. That's a bilinear matter.
Yeah.
Abhijit said the 4-dimensional word identity involves 4-dimensional current, which is not photon, just side by side, right? Side by side.
Yeah,
Whereas,
but these, if I just look at, I mean, if I just start from applying the LSA, so I have all these things and then I have a photon. So that will come from Green's function, which will have an insertion of J mu tilde of Q.
The way you think of it is you couple the photon to that.
So the thing is that, so you will have epsilon mu Q,
J
and
couples
then
to photon.
you have J mu tilde of Q, right?
Yeah.
So
that's
this
how
I think, I mean,
yeah.
and that precisely is this. So now you take Q to 0.
Yeah. And then all these ways of thinking are the same because that photon then is also dual to the boundary J. So
Right.
Okay, so this is actually, so the insertion of the photon and the insertion of J mu is, I mean,
got it.
so what Sandeep is saying is exactly, yeah. So once you start from the LSN and you get this. Okay, yeah,
Okay, so
yeah.
so if I take what soft photon I mean.
So I will write and then I will also answer at the same time.
At
Okay.
some point, we have to let it go.
Okay, so now actually let me just show that, I mean, why this actually becomes a. So we wrote down these things. So if you now go to the this omega z bar basis, then this actually looks like this. So you have some, you can write some like say a z bar. I will explain what this is, and then you will have this some phi hi. Hi bar, epsilon I, zi bar, ei. Okay, ei is a charge. And this A, this is a soft photon. Okay, so A is the way I define A, it is just limit omega going to 0, omega times A. So it's a plus means it's a positive velocity soft photon times I have this omega z bar, and okay, I can write see my particular form. Okay, so this is my photon. This is and this, if you write, will just simply become your ei divided by z minus zi times you have this E. So this is the thing actually. So now you can see that this, when I just translate to this omega z bar, this exactly becomes a U1 word identity, and you can, this soft photon, so that you can just write as Jz. I mean, by Jz, I mean just the two-dimensional U1 curve. So that is the thing. So once you assume this thing, if you think, and now you can see that the conservation of charge just follows. So Jz is, I mean, it is an operator with h equal to 1, h bar equal to 0. Okay. So the point is that now from here you can easily, I mean, just standardly you just do the contour, and then that gives you the charge conservation. But the point is that you also get an infinite number of other constraints from here actually. I mean, which turns out to be very powerful. Now the thing is that the jump from here to here, I mean, no one actually has asked you to interpret it in NISER, but if you do that, then you get, it turns out that it is quite powerful.
And what are the what did you get? What are these other constraints physically?
Well, I mean, other constraints means, so you can find out constraints on the S matrix.
And these are
So these are actually basically sort of the Bootstrap, the S matrix, using this infinite dimensional.
No, but some physical other constraint. So higher soft theorems or something.
No. I mean, these are not the higher soft theorems. So this soft theorem just becomes your U1 Kac-Moody algebra.
Okay. And the infinite thing is that just that Kac-Moody algebra is infinite dimensional.
Yeah. I mean, which was not there in the. I mean, well, to start with, it was not clear that. I mean,
and what is the physical interpretation of these higher constraints? There are just more conserved charges.
Well, I mean, they are all spontaneously broken.
I
mean, that's what it means. Yes.
Okay, but it's not doesn't match to something familiar.
Familiar.
Something I know in some other language.
Language. Okay.
It's just something new.
Yeah, I think it is. Yeah, actually the point is that when Strominger actually found this thing, so what he said that, well, I mean, these are this thing, and then he asked the same question that you asked, and then he said that, I mean, this is this thing actually. So yeah, I mean, either you know this or you know that.
But here we knew one thing, right?
Yeah.
Here we know an infinite number of things. That's what you're
Well,
saying.
the thing is that, I mean, this turns out to be an infinite, I mean, we don't know one thing, I mean, we know an infinite number.
So this is the same thing. These are soft theorems we got.
I mean, it is just a rewritten in a different basis. So this does, I mean, it is exactly, sorry, same as
Same. And the infinity there maps to what here? The fact that it works for every particle?
well, I mean, the infinite number of conserved charges are there.
Uh-huh.
I mean, all of them are spontaneously broken except the local one.
Oh, and that's because it applies to S matrices at every angle.
Yeah, but it is spontaneously broken.
Fine, got it.
Because otherwise you will have no scatter.
Forgot it. I just was trying to count degrees.
Yeah, I mean, that is actually.
Actually,
So it's for all different epsilon, is that like the
No,
I was thinking of all different positions of the sphere.
Yeah, so these are actually the PIs.
Yeah, the PIs.
Which we have.
Because
And
here
these are these ZAs actually.
Here your conserved charges are parameterized by all the moments of Z. So these are directions.
Yeah.
There's some freedom in choosing the polarization as well, right? Like,
Well, I mean, it's a positive helicity who
I was just thinking because this sum over E equals 0 was what you got when you put epsilon equals proportional
yeah,
to Q.
so in this case that epsilon we took a particular form which was actually, if you want I can write that form. Now the thing is that, so here that is actually, so the way you do it is that in this case this global conservation just comes from the fact that since it is H equal to, since it is 1 to 0, so if you take J to infinity, this, I mean, so this has to fall off like 1 over Z square. And that immediately gives me this global charge composition. Now what you can do is that, I mean, like on the sphere, you have all these things, you choose a contour, do the contour and then move the contour to the other side where you shrink it to 0. And both are same.
Sorry, I missed. What is this about the spontaneous breaking?
Oh, the thing is that the only the charge which annihilates the vacuum is this J naught.
Uh-huh. So the other J ends.
Yeah, they do not annihilate the vacuum, so they are all spontaneous.
Okay. But just looking at this, can I then just say that you have a Kac-Moody algebra, etc.,
Yes,
etc.,
yes.
all that is there?
Yes.
But you maybe don't have unitary representations, etc.
Yeah, that is a different question. For that, actually, one has to compute the JJ. So you have to have two soft photons. Okay, so once you know the multiple soft photon here, so that should give you what is the K, which is in the JJ. Now at tree level, if you do the tree level, at least so far, what one gets is K is equal to 0.
So what is the meaning of spontaneous symmetry breaking in this two-dimensional language?
Well, so that so the point is that, so I mean, if you just as Siraj said, so the conserved current is Q of the n. So these are just like this these things, right? So you have Z to the power some n Z to the power n times J. Right? So it is only for n is equal to 0. So this Q of Q0 actually on the vacuum is 0, but then for the other it will not.
Okay. So it's not like you have some grading structure that for half the ends it annihilates.
No.
But not, huh?
That is still true, but the thing is that what I mean, so this n negative. Okay, so that is, those are still there, but the point is that the only thing which is actually, well, I mean, yeah.
Positive ends don't annihilate. No n annihilates except for
No,
0.
that's what I was asking. Like for usual.
It is a usual
Like
half of one side,
what
yeah.
you get actually.
So half of them annihilate and
Well, half of them annihilate, but the thing is that if I consider a CFT in and out, then those half will not, I mean, which will actually annihilate. So the only things which actually annihilate both the in and in that
both the
north
okay.
and south.
Oh, okay,
I have
okay,
two
okay.
vacuum here, right?
Then that
Yeah.
the only one there.
Yeah. So the only one which will is the Q. I mean, that's what I mean by the rest are all spontaneous.
No, only one side is supposed to be annihilated, right?
No. But I'm saying, I mean, if you insert a CFT, like if if I have something like this, something that one.
Yeah.
So one is at 0 and the other one is at other one is at infinity.
Yeah.
So this q in this n for less than 0, so they will not annihilate the vacuum at infinity.
That's the usual story, right?
Yeah. So they are, except the q naughts. I mean q naught will actually annihilate both the vacuum.
That is again the usual story, right?
Yeah. But I'm saying that, I mean, and this is the charge of the QVT, I mean, which you see, the conserved charge. So what I'm saying is that we don't have more than that actually. So if you just look at the conserved charge which you find, it is just the global here.
Yes.
And then the rest are all spontaneously broken in.
This is what I'm not understanding. Qn with n positive kills the vacuum, right?
Yeah, I mean so Qn, okay. Yeah. Yeah, for n greater than for n greater than 0, greater than equal to 0, they actually annihilate.
That's usually that's how you define
but
the
thing is that,
vacuum.
but then you also have this thing, right? I mean,
No, you don't have that. You don't
no,
have
but you
Qn
have
positive
to
greater.
annihilate both the vacuum actually.
Why?
Because otherwise, how is it going to be a global?
So I think what he's saying is that if you look at
it is.
just look at correlation functions and ask which charges give you homogeneous relations between correlators. Okay, only SL2 are there.
No, but insofar as that, whether the vacuum is killed by charges or not,
No,
which is a test of spontaneous symmetry breaking, that is just like usual, right? These charges
No,
also kill.
It is, but you know, one of the usual outcomes of a non-spontaneously broken symmetry is that correlation functions obey homogeneous relations. Right?
Okay.
That you take a certain correlator and do a transform only on that, don't involve some other correlator, and you get a relationship.
Okay.
That happens for SL2R or for K0 here, but not for the other guys. Because you cannot take the thing around and close it. You need to.
Yeah, I mean, because if I can do that, then actually that.
You can commute the Qn through and then kill that one, right?
No.
But then
So this Qn, now if you take Qn with n greater than equal to 0, so this is not equal to 0.
But this is usually the story, right?
Yeah.
This is usually the story. So you are not, I'm not seeing the difference.
maybe another way of saying it is that the charges that kill the vacuum are not Hermitian.
Yeah, because Qn dagger. Yeah.
Because no other Hermitian charge kills the vacuum.
Yeah.
Ln plus L minus n, that doesn't kill the vacuum. You know, something with real eigenvalue.
When we build representation, unitary representation of Kac-Moody algebra, that's the condition we put, right?
I mean, it's so sorry. No, it is a condition we put, but I mean, he's saying that we have a certain notion of non-spontaneously broken symmetries. Right? One point is that it kills the vacuum, but another thing is this correlators. So I'm saying the main difference is that the things that kill the vacuum are not Hermitian.
Yeah.
Because
so
I'm just trying to understand how this algebra realization is different in this two-dimensional case than it is
not
from
actually.
the other two-dimensional cases.
It is not actually.
Okay.
It is
So
the same.
would you say that Kac-Moody, the WGW
Well,
model also has a spontaneously broken Kac-Moody symmetry?
Well, I mean, that's the term.
Okay, fine.
yeah,
Fine, that's fine.
I mean,
That's fine.
I mean, that is
we often say this, right? We say only the global part of the conformal algebra.
That's
Because,
fine. I mean, this is a suitably
uh,
generalized notion, but
yeah.
okay.
Actually, just from the ln, actually, I mean, if you just write this, I mean, the usual argument, I mean, these are for n not equal to 0 plus minus 1, these are not globally defined.
That's fine. Yeah.
So it is exactly the same thing that I'm saying. I mean, so, but this language, because in this asymptotic symmetry, they talk about spontaneous symmetry breaking, but it is not exactly a spontaneous symmetry breaking, but that is.
What seems interesting is that you still have half the generators annihilating the vacuum, but you don't have a notion of unitary representations, right?
Well, I mean, we can have a
Like
notion of.
sometimes those conditions come often because of unitarity, right? But here it seems because your k is coming out to be equal to 0.
Well, it is at tree level, this k is 0 actually.
Yeah.
I mean, which of course, which may be
I
expected.
see.
But the point is that unfortunately, I mean, no one really has found that k, which is here. I mean, there are many that k could be a number which depends on the infrared cutoff of the k. I mean, once you go to the roots. So there are various discussions like this. But the point is that, okay, I mean, I have actually talked about this thing many times.
Go ahead, I'm so sorry, please.
No.
Yeah.
I mean, no, it is most important that, because it is what I will say is an extension.
So,
of
sorry, Shamik, it's a remaining
Yeah,
question. For k equal to 0, if you do representation theory of the Kac-Moody algebra, then you don't find short representations, right?
No. Okay. Yeah. I mean, for these actually, but for the gravitational case, it turns out that, I mean, that algebra is much more complex than this, which has this super translation and even SL2 had. That has actually no steps.
Okay.
Even that does not have
steps.
yeah. Because then that actually, so that's what I said. I mean, the power, I mean, the way you can do is that you can actually try to bootstrap these things. I mean, using this way, and it has to some extent been done. But I think more serious people who think about bootstrap a lot, I mean, they should take care of the rest actually. Yeah, I mean, bootstrap is a very, I mean, this is, I think, the final use of this thing actually. Yeah. Because, I mean, I don't think anybody is going to.
Shamik, though I may be the principal offender, I think you should feel free to say, we'll postpone questions and complete what you want to say.
Well, actually, I am actually far away from that. So actually, I think I just clear up all the doubts.
Okay, fine. That works.
I think, no, I mean, that is a very important thing actually.
Maybe you can talk about the new structure you found directly.
Yeah, okay. And it is actually exactly this here. Okay, so now actually, of course, this current, so the important point is that these soft operators, which is God, so these are actually basically two-dimensional currents.
And they were spin 1 and holographic.
Yeah, for photon it is spin 1 and holographic. Now the thing is, so this is the main thing, and then the thing is that, so once you have this thing, you get an infinite extension of the symmetry, and the thing that you can, I think, do most efficiently using this is try to bootstrap. And why it is most here? Because most of the bootstrap thing can be done only for the massive case. When all your external particles are massive, because once you take it massless, all of your things will just break down, right? But in this way of doing this thing, that does not enter. I mean, there is an issue of infrared divergence, but that also seems to some extent under control now. Oh, I have already talked about that also here. So that is here. But okay, so let me now talk about this thing, which is the gravitation. Okay. Okay, so the graviton, soft graviton. Okay, so you can define a notion of what is called an OP, I mean operator product expansion. So this is my H2 and I have these operators here. Okay, so say phi 1, phi 2, and so the collinear limit of the S matrix, that translates into the OP on the celestial sphere.
Right. And the collinear limit is one that the IR people find very complicated.
IR people, yeah.
There are new divergences.
Yeah, I mean the point is that, yeah, I mean well, collinear limit, yeah, collinear, I mean once you go to the loop, this IR and collinear, they will interfere.
Right.
And then there can be a, but let us say I'm just talking about the tree level.
Right.
Okay, so all my discussion, because then, well, I talked about it, these logs and higher things, so those things are here, but I will not touch those things now. But these are all tree levels, so let's first look at the tree level.
But just for orientation, in QED are exact statements known about the nature of collinear divergences, or is it just loop by loop?
Well, I think the point is that what we are mostly, yeah, I mean see, if you want to do this thing, what you need to do is actually the collinear limit between a soft particle and a hard particle. Okay, and that can be obtained from the soft theorem.
Right.
Now, these soft theorems, I mean, now actually, of course, these logarithmic soft theorems are there, which are claimed to be, well, proved only for the log omega A, claimed to be universal and real. So for them actually one can do. However, one question which has never been here is that first I can make soft and then take the continuous or the other way. At the tree level they match. Do they also match at the loop level? Now that has not been checked, and I talked to people. They are sort of afraid of.
There are serious doubts you're saying about it.
They say that nothing will happen, but the thing is that I don't think anybody has.
Who's they?
Huh?
Who's they? Is it the celestial crowd or the IR?
No. These are not the special crowd. These are the eccentrics
Okay.
crowd. Crowd actually. Yeah. So the thing is that. So that actually they say that however this needs check.
Okay.
This needs a serious check actually.
Yes.
Because lots of things can happen at the loop level. We don't know. Okay, so but let us just talk about the tree level. So this is what actually translates into, if I have collinear limit in the bulk, then that translates into OP.
And not to slow you down, but
No.
precisely what is the collinear limit that you're
Collinear
thinking is
limit,
coming out in the momentum?
They move almost in the same direction.
And then intuitively you sort of replace it with one particle.
One particle, yes. Precisely, and that is the OP, like something times something is something. Okay. So that's the structure. Okay, now the point is that you can do it for the graviton. Okay. And the answer that you get is the following thing actually. So
These are two gravitons then?
yeah. No, these are hard gravitons.
Hard gravitons.
Yeah. Yeah. Well, one of the things which is a diagnostic of this fact that whether these limits could match or yet is the problem that suppose at the loop level they don't compute. First I take soft and then collinear, or then first I collinear then soft. Then what could happen is that the algebra will not close. Many things could go bad. Okay, so I have written only the similar terms in this OP. So this is the tree level answer actually. This is what you get. Tree level, actually it is not exactly a tree level answer, it also holds at the loop level for self-dual gravity where the amplitudes are both in and finite. There is no OP actually. So as long as, so this is actually the answer. You can see that there is a pole in the Z12. And now this is the beta function actually. So this is okay. Now what you can see from here that this beta function has poles at different values of these delta. So like delta 1. So if I have delta 1 minus 1 plus n. So the first pole, since n actually starts at 0, it starts at 1. Okay, so this you can see that it has poles at delta 1 equal to 1, 0, minus 1, minus 2, and all these things. Okay, so you can define a soft soft operator by taking the residue at the pole. Okay, so suppose I have this thing, so I can define.
So that's roughly like putting, instead of a photon operator, that photon operator with this funny value of with these integer values. Meaning,
Yeah, I mean, right. So these are actually all integer values of it.
So
I
not
mean,
physical
these are-
photons.
Okay, no. So these are now
gravitons.
Yeah.
Not physical gravitons, but these complex continuum gravitons, right?
No. I mean, these deltas are all real.
But I thought physical things were principal series.
Well, I mean that's the thing actually. So the principal series. Well, I mean, physical means.
Meaning what you get.
Yeah, the thing is that
real.
So you start with 1 plus I lambda, and then you can actually analytically continue.
Yeah.
And then you find these poles.
Yeah.
Actually.
Yeah.
Yeah. So in that sense, you can
Yeah.
say that these are not physical, but these are the important. I mean, these are the things. I mean, so delta is equal to 1 is physical, which you can say equal 1 plus I lambda.
Yeah.
But starting from after that, it is not. Yeah, and then you can actually say that okay, I mean these are unphysical, but this is the one which actually gives rise to the your SL2. So this delta is equal to 1. So that is the conservation of energy momentum.
Can you please say where is this OP statement coming from? Is it coming from looking at the asymmetries of
Yeah. I mean, these are actually, so these, the first term, which is this 1 over Z1, 2 times this thing. So this was actually found by Barn and Lie from Algebraic. And these other terms, I mean, they just simply follow from the SL2 or invariance. Okay? Because if you look at this, I mean, they have exactly, they are, the SL2 are descendants actually. I mean, they are all Z bar 1, 2. And then you have the A bar 2.
So the first term that you said, that is like replacing 2 gravitons with 1 graviton?
1 graviton, and then the rest has to be there.
But the rest are like, can they be interpreted as the like insertion of some other thing?
Yeah, I mean, you can think in that way. Yeah, I mean, you can think, I mean, just you are replacing this whole thing by this here. So the first term, which is this term actually, so Z bar 1, 2 by Z1, 2 times your G, delta 1 plus delta 2. Okay. But then the thing is that the invariance is like SL2R cross SL2R, and then you are using the SL2R right invariance to get the rest of the terms. So it is just that.
So I was just trying to understand what does it mean in the amplitude. So what's the
So the amplitude, I mean, so the amplitude you can just, I mean, from the amplitude you get this whole term actually. Okay, so you just expand and take the
But it's some analytic, right hand side, the other terms are some analytic continuation of S-matrix.
Well,
Because
the
they are physical.
analytic continuation in the sense that, so I have done this integral with these deltas, and I can, if I do an analytic continuation, then I get these poles.
Yeah.
But I could stick to say delta 1, delta 2 is equal to 1 plus I lambda, but even that, in that case I have to do analytic continuation, you are right, because of this.
I can think of this as 3-point scattering, right, in some sense.
Yes,
Rather than
yes.
3-point
I mean that
scattering
is right. I mean that because I mean these are the structure constants. So I could
Now
take
for the
this.
leading guy, right, because the rest, as you say, fixed by the symmetry. The
Hmm.
leading contribution, you can think of some sort of a 3-point function.
leading contribution, I mean you mean this one?
Yeah.
Yeah, for that actually the point is that you have to do some shadow transformation to find it exactly to
No, but
identity
it comes
that-
from the 3-point scattering, right?
No, it does not come from the, I mean, the 3-point scatter, I mean, you can start with a 4-point scatter and then you can reduce it to a 3-point scatter. Okay? But if you start from a 3-point scattering, then you don't have anything, right? I mean, you just make 2 of them linear, then 1-to-1 scattering is just 0. So, in that sense.
And there are multiple 3-point structures, right? This is the Einstein gravity.
Yeah, this is the Einstein.
But you could have plus alpha plus beta.
Yeah, those have also been checked actually, and do that, and they give rise to different kind of these things actually.
Only the leading, the rest is descendants, right?
The rest is fixed by the data actually. I mean, this is like SL2 invariant.
So just to understand, so I would have thought that just from your analogy with the photon, that one way to understand the conservation of energy momentum would have been just to look at the analog of the soft theorems.
Yeah, and this is
a restatement by analytically continuing your data.
Oh, no. So, I mean, if you just want to I mean, if you just want to see the, okay, I mean, I did not go
because there
in that
you're
way.
on shell, right?
Yeah, so I did not move in that way. So, there are two, I mean, one is this one soft graviton theorem. Okay, so, and then there is this Catcher-Stropinger theorem. I mean, which is the subleading soft graviton theorem. Okay, so this so this gives you just like the conservation of charge forward from the So this gives you the sum over T is equal to 0. Okay, and this gives you sum over J mu equal to 0. Understand?
J mu mean?
Yeah, the angular momentum.
Angular momentum. I see.
Okay. So that's how it works.
I see. And that's the more, that's looking at the asymmetry.
Yeah, but this is actually, this way of looking at it, I mean, that gives you more power because of the particular thing, because this Weinberg that corresponds to delta is equal to 1, this corresponds to delta is equal to 0. But the thing is that it turns out that you have not poles not just at 1 and 0, you have poles at all negative integers. And those actually combine into this W infinity. Okay?
Additional constraints.
Yeah.
Is there an analog just for QED that you get by looking at off-shell? So
the point is that once you take the loop corrections in the QED, so then actually we have shown this thing, that actually you also get a higher spin algebra, and at the classical level that actually closes into this W infinity algebra. But in QED you need the loop effects. Yeah. So
I see. Here you get in classical.
This is for GR. For tree level GR, you get this infinity here. But for QED, if you want to get this kind of structure, then you have to go to loops.
Thank you.
So one more thing about that OPG. So is it that the higher order things are like subleading in the coupling constant or something? Because for instance, if
which higher order you mean?
N is equal to 0 is replacing 2 gravitons.
No, there is a coupling constant which is kappa over 2.
That's 4 already.
Yeah, and the thing is that so all of them are of the same order in kappa, because the first term, I mean, this is the SL2 or descendants, right?
Yeah.
So they will not have different powers of K.
So I'm still trying to understand that if you take, let's say, 2 scalar going to 2 graviton amplitude,
okay.
If you take the 2 gravitons for linear, you can replace those 2 gravitons with, let's say, first term from here being 1 graviton.
Okay.
But you're saying that you still miss out on an infinite more things that are at the same order in the coupling constant as well.
Yeah, I mean, these, no. I mean, we don't miss out actually. So that also, I mean, this also comes from the expression. But I just said that, okay, I mean, once you get the first term, then all the infinite number of terms, those are all fixed by this. I mean, they're all descendants of the, I mean, SL2. You can just look at this structure, right? I mean, there are L bars and these things. So that is fixed by the SL2. L law and signaling essentially. Okay, so that's what I mean. But you also, I mean, you get those terms from there. I mean, you have to get those terms.
When you said that there is this W symmetry, it's chiral symmetry, right?
Yeah.
So that's happening in which variable? Z.
That's happening in the variable Z. Here, actually, you see that this Z bar is just bookkeeping. So you have poles only in Z.
Okay. But what is the role played by Z bar?
Okay, so that is.
So can I mode expand in Z bar and obtain infinitely many W?
No. I mean, I come. I mean, so this actually. So if you just do this. So now, suppose you get this H1, okay, which is the Weinberg software. Let me just write this thing. So this is what you get actually. You get sum over this looks like this. For example, if you just take the H1. Okay, so the way you do it is that from here you can see that it is a single power of Z bar. So what you will do is that you will write this H1 Z bar and some H1 minus half plus Z bar H1 plus half. These are functions of Z. So you get a doublet, and these are doublets of the SL2 right, and which is the Z. So instead of one content, you get two contents, which are these, which you can write as like H1 alpha. Alpha is the spin of rotation.
And the SL2 acting on it commutes with the W.
Yes. Okay. So that is a different. So this alpha index comes from the Z part, the SL2 attack. For that, it's a spin half. Okay. Now, if you go to H is equal to 0, you get a spin 1. So you get 3, which actually form this SL2 hat. Okay. So that's how actually you get this.
What? Sorry, the H1 has 2.
H1 has 2 components. It goes up to 2.
Yeah.
Okay. Now, if you take H0, then it's a cubic. I mean, it is actually quadratic in Z. Okay. So H0 Z bar. It turns. I mean, you can just take the residue and just it is actually quadratic. Okay. And then this will actually turn out to be some J 0 Z. I think. Oh, sorry, J 1. Sorry.
Then this W symmetry relates H0 at H1, right?
H0? Yeah.
W symmetry
Yeah,
relates H0 at
yeah. So H0
it
and
doesn't
H1, and then now if you take H, so you get a spin 1 representation.
Yeah. But what is this algebra? It's a bigger algebra than
Yeah, I mean, but you have an infinite number of H's, right? So now you take H modulus Z bar.
Yes.
So then that gives rise to a spin 3 half. Okay, and so you get this structure. So this structure looks like this. So you get 2, and then you have this, then you have this. So you fill up this wedge. So that actually gives you this wedge subalgebra of the Darwin family.
Okay.
I see. Okay, so that's how it actually works. And the point is that the reason this analytic continuation is important is that this delta is equal to 1 and delta is equal to 0. These two algebras, they actually close. But once you include these, they don't close unless you include all of them.
Nice.
So I missed your point. So here, what happened to the helicity labels? We have suppressed
The helicity is already taken care of. I mean, it is part of this HH bar.
No, but you have only one delta label for each.
Well, I mean, yeah, I just
Is it equal to
last
H bar?
Yeah, it's last. Okay.
Shamik, I mean, as we said, there are multiple structures, so there is actually 2 possible terms that you can write down here.
You mean for
3 points.
3 point function? Yes.
Yeah.
I mean,
And then one can try to play the same game and try to extract the symmetry algebra.
Yeah.
And then one would obtain a suitable generalization of this W algebra, obtaining with a continuous parameters.
Yeah, I mean, W infinity has that generalization. I mean, that it depends on a parameter called lambda, but I think that
2
is
parameters.
2 parameters.
It needs to be.
Yeah, I mean, I don't know. I mean, one has actually.
One of which violates parity, which maybe means with Z.
Yeah, the only condition that one has to satisfy is that you will have pole only either in Z or in Z bar. If you have poles in both of them, then actually you are. Okay, I mean, it is that is not a structure actually. So these algebra.
Does this have the central extension?
And these, no, but these algebra has non-trivial states actually.
Just at 0 central.
Yes.
Okay.
Those actually we have all found. Like these algebras we have found by us in these 0 and 1.
Okay.
But then we did not understand. We did not have these picture actually.
It's the wedge algebra.
No, yeah, this OA algebra thing was, I mean, we did not start with this. We started with the soft theorem. And that is the point actually. So we found these three in fact. But then the rest of this thing, this actually comes from this. And
sorry, this is just to make a contrast. You started with soft theorem, and this is about 3-point function.
Yeah, I mean,
without any soft theorem.
Soft theorem gives you these three. Okay.
But once you have that, you can take pole anywhere you want.
Not from the soft theorem. You have to start with this.
Okay.
Because soft theorem is already giving you the residue at the pole.
So it is that kind of thing that you were saying that the infinite dimensional algebra previously we were discussing.
Yeah.
That was not clear.
No.
In the soft.
No. This was actually clear. For example, so this gives. Okay, so this H0. So these, I mean, this gives you this SL2 hat. But the thing is that this double infinity is even much bigger than that actually. So this has this SL2 hat, and then this thing. All of these things, and then we could not actually, we did not understand that how to make sense of this because this algebra did not close. Okay. This actually gives you the PLS, then this double infinity actually. But in any case, the thing is that this has a very rich structure, and what we showed was this H0 and H1, which is H1 gives you the H0 gives you this SL2 hat, and H1 this super transition. That has null states, and that gives rise to the differential equations for this energy. But then if you want to do it for the cell dual.
Sorry, but when you talk about null states, the norm defined is the same.
Well, by null state I mean it's a primary descendant actually. So we don't. I mean, it's not that.
It's not zero.
Yeah. I mean what we. I mean it's a very. Like I mean it's a lot of PA in the sense that I mean you have to take the linear combination and see which of them give you. So it's a very unsophisticated way because the definition of the norm is something which is actually missing from this algebra.
Right.
Okay.
And
But null states you can define as this primary descendants. You have to do some work. But if you have the notion of a norm, then that becomes much.
So one can try to see whether the linearity of the S matrix is consistent.
Yes. I mean, it must be something which is related to that. Because the thing is that the null state definition is that I have this S matrix, then I substitute the null state here, then that gives me 0. So that's the point. Okay, how much time? I mean, do I have time? Oh, I have 20 minutes.
But maybe your main punchline, sorry, just...
No, punchline, actually you have basically...
So you're going to talk about higher spin extension.
I was thinking of talking about this.
Okay, up to everyone, but it would be nice to...
Even higher spin.
Even higher spin actually. So this W, so now actually the thing is that you get one W infinity. Now in ADA, so this actually this, I mean, this was actually basically the motivation for that actually, for just looking at this type, that's what this thing, because in it, and actually one thing, I mean, which is actually something which somebody probably someday will clarify, that this has something to do with this ADS3 CFT2, because the point is that so in the ADS3 CFT2, so this Gabriel, Gopakumar, so they actually found a very interesting thing, what they call this Trini higher spin, or this higher spin square. Okay, so instead of, so they have actually two W infinity algebras. Okay, I mean, and which is much more than the Vasily theory. And that, I mean, which is actually they show. Now the point is that here, so what you say is,
it's not, I'm sorry to be so ignorant, it's not just a left moving and a right moving.
No.
It's much more complicated.
Yeah.
This is in the tensionless limit, or?
Yes, precisely. So this gravitons, this basically soft gravitons. So that actually gives you one W1. I mean, this is a small W1. Okay, not, I mean, this is the contract, I mean, the contracted, the classical W1 plus infinity. Now the point is that actually now you can actually generalize this thing which we did to the higher spin algebra, and that algebra actually looks like this.
But this is not restricted to some, this is in 4D also. Yes.
This is in 4D.
4D, yes.
Asymptotically flat space actually. So in 4D asymptotically flat space, of course, we don't have interacting higher spin theories, but there are some examples of these idle theories which are non-imitative. And so non-imitative. Well, so this is actually a higher spin extension, but I'm just saying that okay, these Vasily theories are not there in flat space. They are only in ADS and DS there actually. Actually, I don't know what happens in DS because some of these things which there must be two W infinity somewhere. They are also actually.
In DS.
If you just analytically continue. Yeah. In DS3. Not the Vasily, but there was some higher spin algebra in DS3, which is an analytic continuation sort of feature copies of this. Okay, so this is the higher spin extension which we propose. This is sort of the minimal higher spin extension. So sigma 1 and sigma 2, these are the helicities. So we have the same structure.
G is a graviton.
No. For sigma 1, sigma 2, it is a graviton. But now actually, this, I put restrictions on this sigma, which will come out.
So these are higher spin.
These are actually.
Now you actually have higher spins in 4 dimensions.
These are 4 dimensions.
You're looking at scattering of high spin particles in 4 dimensions.
The thing is that we did not, scattering is 1A, but the point is that the OP which I wrote down, that can also be analytically continued in spin.
Oh.
That's.
So you're not imagining that they exist.
No. The thing is that what we are writing down is the analytic continuation in spin. It turns out that you can actually, and I will explain actually. That is, okay. I think in the remaining time, I will explain. And then.
Massless higher spin?
Yeah, these are supposed to be massless higher spin. Okay, so this is the structure, which you can actually write. And the point is that here you can see that the structure is like, so G sigma 1 times G sigma 2 gives you G sigma 1 plus sigma 2 minus 2. So once you introduce a spin 3, you have to if you want to close your OP, then you have to introduce all the hierarchy. Because
just like Vasily.
Yeah, it is just like Vasily actually. Okay, so actually we put the restriction that sigma 1 is greater than, sigma is greater than equal to 2. Then also it will close. Or you could introduce sigma equal to 1. But the point is that we put this restriction on the okay. But then you can see that you can have 2, 3, 4, and they will close only if this infinite number of E is there.
So just even is sufficient?
Even is sufficient. Yeah, I think 2. Yeah, if you take it to be 2. Yeah, if you take 2, 4, 6, 8, then that also will close actually. Yeah. But the thing is that you have to have an infinite number of them. That's the main. Now, where does this algebra actually follow from? So you actually, and now actually I will not show that. But the thing is that, so now this actually gets extended into, you get a much bigger algebra that weight sort of extends in this direction. And what you get is you get one copy of W1 plus infinity, which comes from the spin 2. and then you get a W infinity which comes from various values of the speeds. So you get one W infinity from spin Q. I mean, which is the old one, because that is contained here, right? Because but then you get a W infinity from all the higher speed particles. So this is the W infinity which comes from this. So you actually indeed you get a W infinity and a W1 plus infinity, which actually is, I mean, that's the most natural extension of this higher speed algebra. I mean, of this algebra to the higher speed algebra. Okay? And now,
So Shamik, sir, I don't
Yeah.
know much about this W algebras, but are they Lie algebras?
they are Lie algebras, yes.
I mean, at least this W3, etc.
No, I mean, there are W3 is not.
Okay, but this
No,
W3.
yeah, so if you fix, I mean, if you cut it off at a particular spin, then it's not a, I mean, it's not a Lie algebra, but the Jacobi identity works. Yeah, that's the thing. Actually.
Maybe make it a Lie algebra by saying every product of two things is a Newton.
Yeah, but then actually you are essentially,
Yeah.
I mean, extending.
I'm not sure. That's
Yeah.
how you can get W infinity from W3.
Well, I mean, but it tells you that, I mean, you have to add higher spin,
Yeah.
because you get objects like T times T, I mean, which is like spin 4.
Yeah. But that's W. You can think of it as W infinity. That's something.
Well, I mean, I think you need an extension. Yeah, I mean, that is. But the one thing which is clear that Siraz said actually, that I mean, you need the fact that you need higher spins flows, or otherwise you have to introduce these composite fields which are there, which already appears in the Lie and it's a Lie algebra. But this is a Lie algebra. I mean, these are all infinity, and there is no problem with this actually. Now these higher spin particles, they themselves actually give rise to a W infinity, which is actually very similar to what happens in the ADS3 space, because which was actually shown by Thyssen and these people. That how, I mean, that was long ago.
So all of that happens from the boundary gravitons in ADS3.
Yes. I mean, they have a Chern-Simons theory for the higher spin also. Okay, and then I mean,
So these new charges are all built out of boundary.
Yeah.
So similar to here.
Well, here of course it is not clear. But the thing is that what I am saying is that the algebra, now actually I will show that, I mean, why I think that we should take this extension seriously, that the OP which I wrote down, that can be analytically extended in spin actually. I mean, continued in spin. And the reason is that the following. So I could have written this here in this. Say I am just focusing on the graviton case. So I just write this as a GP. And because of this, actually this holomorphic factorization, you can actually do this thing, this extension, analytic configuration. So you can write the graviton OP in this way. It is a very nice symmetry. Instead of writing delta sigma, you can write it in terms of
W literature, do people group the generators into Z-bars?
I mean, the point is that if you look at the wedge subalgebra, then they do, yes. I mean, in fact, the point is that this is the Polyakov, I think, this goes back to the two-dimensional, this SL2R symmetry of the two-dimensional gravity. Okay. So it goes back a long way. In fact, the thing is that this SL2R hat, that is precisely what one gets in 2D gravity in the item range.
So I would just ask, in the ADS3,
Yeah.
if these higher spin charges are basically built out of multi-boundary gravitons,
No, I mean, no, I don't. Well,
If it's all coming out of
yeah,
boundary graphics,
no, I mean, it does not come from the. I mean, what do you mean by it all comes from the boundary graphic? I mean, you mean it just like TT.
Yeah.
No. I mean, so you have gauge fields. I mean, in ADS3, I mean, what I remember, you write down a higher spin Chern-Simons action with higher spin gauge fields in the
and
bulk.
higher spin bulk.
Yeah, and then you look at the asymptotic symmetry of that. That becomes this.
Okay, so you get this once you also have high spins in the bulk.
Yeah. So this one actually is that part actually.
Okay.
Okay. And this one comes from purely from the spin 2.
Okay, got it.
Okay, so that's how we get this.
So then I should think similarly here that I'm actually
Yeah.
putting high spin
So
fields in the
this
bulk.
one actually should come from the asymptotic symmetry analysis in the asymptotically flat.
Because you have higher spin fields in the bulk.
Yes. But then you have this more exotic W1 plus infinity which comes only from the spin 2.
But massless high spin fields in the bulk.
Yeah, these have to be massless.
There aren't there all these theorems that they cannot.
I mean, these are actually, there are some chiral higher spin theories which people have.
Yeah.
I mean, you don't have massless higher. I mean, you don't have a Vassiliev theory. I mean, these are interacting but non-unitary.
But even in the bulk, not unitary.
Yeah.
Okay.
Okay. So in fact, okay. So let me just write down this thing. So you get G. Okay. Sorry. Okay, so you can write it in this way, and now you can see that these OP coefficients, they only depend on H bars, and they don't know about H. So for any choice of H and H bar, I mean, even if I just forget about this thing, okay, and then this is actually true for any choice of H and H bar, and then that gives rise to this. So this is the simplest analytic continuation in spin, and which will give this thing.
So this format is same with this format.
Same. Yeah. So that is the most natural analytic continuation, which has two copies of this here. Yeah. But I think this is weaker. I mean, because of exactly this thing that there is not. I mean, so far the theories which are known. But this people talk about this tangential strings. I mean, they can't be non-unitary.
Actual string theory and algebra going to infinity. That.
Yeah.
Okay, but you have to make sense of that.
Yeah, but like the thing is that this Grossman, I mean, this is like at the high energy. Yes.
Yeah. So somehow you have to make sense.
Yeah, and the thing is that I mean, so these kinds of algebra. The thing is that I mean, these kinds of algebras arise naturally in this sense actually. That all these OPs, because of this fact that so this part is purely determined by the SL12 right. So it does not know about SL12 left. So I can change my scheme that way. I mean, that is essentially the point.
Sorry, I forgot where this distinction between left and right happens.
Oh, because I mean, you have a pole in Z1, you don't have a pole in Z bar.
But it should be, one should have that. Right?
No, I mean, these are all chiral.
So where is that 4 dimension? Where is it coming from? 4 dimension?
Because I get plus. I mean, these are plus helicity.
But there is an alternate.
Yeah, I mean, there is an, okay, so you have G minus G minus. There you have pole in Z bar.
Yeah.
Okay? Okay, and then.
So that's a bigger symmetry also.
Well, no. I mean, you have a pole in Z bar, but no pole in Z.
Yeah.
So you can say, I mean, it's a W bar.
Yeah.
And just a copy of that.
No, but the SL2 that was acting here is the same in which that is the SL2 bar, right, in the other side.
Yeah.
So it should kind
this-
of play together and maybe make a bigger symmetry. even
Yeah,
if
so
it's-
that symmetry we still don't understand. In fact, the point is that you could ask that what happens in this case. I mean, if I take plus and minus,
Yeah.
then you get both pole in Z12 and Z bar 1. And actually, we are still, I mean, it's part
But
of
it
our
should be like a bigger symmetry.
It is a much bigger one.
So is the claim that your symmetry algebra will be a symmetry of string theory in the SQL state?
I mean, this is, see, I mean, the fact that this contains these two copies of it, I mean, which in ADS3 somehow related to these tangential strings, could be, I mean, once we
That's
make
not very
sense of,
Priyadarshini is
Yeah, I mean, so they actually, yeah, I mean, I was thinking,
Yeah.
I mean, they actually, so they, I mean, I don't know if you have found these kinds of higher spin symmetries. I mean, those should be there. I mean, they are, you know, so,
In this meeting, you guys invited me to, there was this really interesting talk by the person who was doing string amplitudes, Steve.
Steve Barger.
Ah.
Yeah. So this Steve Barger, yes. So they will say exactly, I mean, this kind of thing. I mean, exactly this kind of thing. I mean, they. Well, I mean, he was doing it from the scattering.
Yeah. I mean, does he? But
If you
look
take
at
the
example
high
and
energy-
see the symmetry.
Well, I mean, that I don't know.
Okay.
I mean, they have. I mean,
They don't think that.
So, but
Yeah.
string theory should have many higher spin current for one spin, right? This is one higher spin for one spin.
I mean, what do you mean by one higher spin for one symmetry?
String theory spectrum,
Mhm.
let's say 17, spin 17, take massless limit.
Mhm.
You'll have many fields there.
Many fields, yeah.
So here, but you will have only one 17 spin, right? I mean, the way you were closing it, 2, 4, 6 and all that.
No, actually, so what do you mean by many fields?
Hang it on.
Just hug it on, bro.
Okay. Yeah, I mean, those are, of course, there. I mean, I'm not saying
So
that
it is even bigger, I was thinking.
Yeah, it could be bigger. But so what is exactly what?
Maybe
I
it's
mean, the
sub-algebra,
thing, see,
maybe
the
it's-
thing is that
The lightest guy at each spin makes this.
So actually, I have to actually see.
Yeah.
I mean, I have to understand that test that what exactly happens in the ADS3 actually, because in the ADS3 you get an algebra which is generated very easily. So that actually I have to understand.
So just to understand, what is the consequence? So suppose we have the Zero Shapiro or Venetian or whatever amplitudes, and I take the limit where all energies are much bigger than the string tension.
Yeah.
Then this infinite symmetry has some consequences.
Yeah, I mean, this is what Gross and Mendes showed, right? In fact, I
Sorry,
mean, not
I'm
Gross,
so
but
ignorant.
Gross actually. This short is actually that how these scattering amplitudes, they are actually connected to each other if you take this high energy limit. I mean, you can sort of get, get everything from the 4 tachyon.
I see.
I mean,
Is that connection due to your symmetries?
Oh, no, I mean,
That's what
well,
is
that
the
is
consequence? Is that?
that one has to see actually, I mean, how this thing actually.
No, because
That's
you're
it.
soft.
No, I'm just saying that I mean that if we have a tensionless string here, I mean tensionless means this high energy here, then there is, I mean, the main argument against this, you will say that okay, I mean, all these things, and there is no massless higher spin theory in the ball in asymptotically flat space, so you have non-unitary things and things. But then your difference will be that okay, I mean I can take the high energy limit of the string theory, and we are all string theorists. So the thing is that, I mean that's it.
No, I was trying to ask the following question,
Yeah.
just in case, which is
I guess.
for the lower cases,
Yeah.
there was an understanding through the S matrix as some kind of soft limit.
No, that actually
Is
we,
there
we
any
yeah,
such
I mean,
understanding?
yes, yeah,
Because then we
there
could
is
relate
actually.
these symmetries.
No, I mean there is I mean there is for these gluons actually, I mean there is something, but unfortunately I mean I could just do the introduction of my paper. But the thing is that yeah, for gluons actually I mean there is this theory I think which was written that in fact we checked that it is a symmetry of this thing. I mean you can write down a corresponding this you can have some Young-Mills charge and then make it higher spin. So this is called this higher spin Young-Mills theory. Okay, you can compute the scattering amplitude there, and that is, and then we showed that this is exactly the symmetry of that. Okay,
This is a unitary or non-unitary?
that is definitely it's a non-unitary.
Higher spin, so it's
higher spin
Young-Mills,
Young-Mills
but not
theory.
for spin
So these are all these twister.
That's like this.
Yeah,
And there
but the thing is
you
that
get what?
they computed just just the MHV 3 point. No, they actually they computed the 4 point. They have conjecture for the end pointers.
So what you did is to
I mean, we take
and
so
then
we
look at-
independently took the scope collinear limit from them. We start from the 4-point function and take the collinear limit from them, and then reproduce this OP.
Them are this Atul Sharma and this.
No, this is not Atul Sharma. This is actually Team Adamo, and also before that actually there. I mean, these are all listed things actually. But that is it. But I think a better way, well, I mean, that was the, in fact, I mean, that is exactly what we wanted to show, that this is a symmetry of some scattering amplitude, which is this, which is shown. But the thing is that this high energy string scattering, I mean, this hard scattering actually, not the rigid, I mean, fixed angle high energy scattering. Now that is, I mean, that is one place where the, well, I don't think anybody has checked. But,
So given that you have this very high symmetry, one can try to construct endpoint functions.
yeah, in fact, actually, Gross in the paper, he showed that, I mean, you can just from starting from the 4 tachyons, you could construct the higher level using this, well, I mean.
No, I just meant from 3 to 4. You have this 3 point, I mean, in some sense it's algebra. Now from here you can try to compute 4-point function, right?
Yeah. So that we can do it.
And then you can take
I mean, we can
the
try to do it. I mean, in principle we can do it.
fixed angle limit. Can you not take the fixed angle limit?
Yeah, I mean that can be taken. I mean that the high energy limiter of those. I mean those are sort of the, well, yeah, I think requires. Yeah, I mean so for those this higher spin Young-Mills theory. So they are, yeah, I mean it is a chiral theory. So that symmetry is this. But I think one should start with the string scattering amplitude and just take the high energy limit, which actually is
Also, another question is that, I mean, you were saying that you hope that it's string theory, but all the examples seems to say that what it is describing is a non-unitary physics in 4 dimensions.
I mean, you mean the high energy string?
No, I mean this notion of null states or whatever this.
No. I mean, this will not define because by solving these PDEs, you get unitary asymmetry.
No, but this is high spin Young-Mills and so on.
No. Higher spin Young-Mills is different thing. Okay, yeah. For the higher spin Young-Mills, we show that it is a symmetry of this. Now, higher spin Young-Mills is also non-unitary and it has some, is probably not completely local. Also,
yeah.
But
I was wondering whether the notion of null states you are imposing is consistent with an unitarity condition, which is not the same as.
No, we have not done any null state beyond spin. So
okay.
I'm not talking about that. I mean, so that check was just check that we start from a 4-point function, you take the collinear limit, and then reproduce this OP in that sense. But what I'm thinking is that because of this ADS3, that it could be that this algebra has some role maybe to play. I mean, if you just understand the idea. Because in the ADS3, I mean, in ADS3, of course, it is this. It is not small w. It is actually capital W. And this, you get 2 copies of W, and then the non-commuting, so the whole algebra. So it is similar here, it is a contracted version of this. So, but yeah, I think the point is that that is something that needs to be understood. But I think even before going to higher spin, the most, one of the important things is essentially this mathematical question of how to introduce a norm. I mean, that is a way to connect to the unitarity.
As I say, and the issue is, so you have S matrices in the bulk and so on. What is the
The question is that, I mean, what is actually unitarity in the field theory? I mean, in the dual field theory. I mean, you ask.
What is bulk?
Yeah, I mean, unitarity, because unitarity should, yeah, I mean, unitarity, I mean, whatever unitarity, I mean, is, yeah, I define, I mean, the easiest way probably is to define a norm using this, such that these null states work out. I mean, if you define this usual ln negative of L minus, then all the null states are 0. I mean, you don't get it. So that is not the thing that you need to do. That we have checked. Then everything becomes 0. You don't have anything. So you need something. But
because C is equal to 0.
Yeah, you cannot just simply define this thing. Actually, in fact, the point is that with a actually Sandeep last time actually, with a complex central charge also one cannot define this thing.
Yeah. In Dissiter there is a similar story.
Yeah. I mean that is actually I think
Dissiter theory is very interesting that way.
Yeah.
But okay, that seems easier to me.
But yeah.
Yeah,
I mean,
okay, we can talk more. I think we should look at it.
Yeah, because I think that was also another like.
But you might be able to define unconventional notions of dagger, which makes left and
Yeah,
right.
left
so
and
on
right
so forth.
actually. Yeah. Some kind
Just-
of
just-
anti-unitary
yeah.
operation which actually does.
Just right, exactly. Okay, so I mean, that would be fun to do there. Nobody has looked at it actually, surprisingly.
So in your case, what is the diagonal motion that comes out?
Let me use that.
No, when you say that it is like a descendant of, sorry, primary descendant, that doesn't,
Primary descendant is just what you define. And the primary descendant that just follows from the word identity that it stops at 1 over z. It doesn't go to 1 over z square. That is all the higher things that it has to keep. So that is the point. But then it does not tell me that what do I do in the daggers. But this this high energy stream scattering is something I don't know how much is known.
There was this beautiful expansion in that talk that I saw. That
This
is the vertical expansion.
Yeah.
You know, I mean, the way he presented it was that the alpha prime expansion is well known to all
Yeah.
others. What he did was the 1 by alpha prime expansion. That looked really beautiful.
Yeah, I mean 1 by alpha.
A systematic 1 by alpha prime expansion of the amplitude to all orders.
Oh, yeah.
As an asymptotic change. Yeah. I mean, such a simple thing to do, but he did it to all orders.
Yeah, and the point is that I think that there actually the picture that one gets is that this string world sheet that seems to wrap the sphere. And that's the natural picture which actually comes up. In fact, that is what one gets in the ADS3 also.
Perhaps
This law. Yeah, I mean, so in the EA, so in the asymptotically flat space, what they are getting is that in the high energy, your string world sheet will wrap the shear spheres. And there is some localization.
This is the Grossman picture, right? This is Grossman.
Well, I mean, the thing is that I don't think that is very well. I mean, that is the type of EA actually that one should get. I mean,
Because the saddle points are the same as
no,
the
I don't think. I don't think they have shown that. What they did, they took the expression for the amplitude and then they expand.
They expand it. They get an answer. But you are saying this picture of the string.
Yeah, that
basically some
seems
saddle
to
point.
come from the EA, but it is not exactly the. Well, I mean, it may be exactly the Grossman EA, but no, I don't think.
Or some, if Grossman they made a mistake, it has to be some version of that because you're getting a picture of the saddle point.
It is because the point is the Grossman they probably just. I mean, mistake no part.
I don't know. I mean, whatever. If
No,
you're saying it was
these saddle points are right because all those things actually are the same as the CHY. I mean, so and that gives you the right answer. I mean, although in completely different context. I mean, CHY is the alpha prime going to infinity. Hey, alpha prime going to C is equal to say of just the.
Why do I have a feeling I read the abstract of a paper that said Grossman they had made some mistake.
Oh, the small mistakes.
Small
actually
mistakes.
that people make. I mean, these are all conceptual. I think the thing is that we are talking about things which are all of order of magnitude.
Some high level factors of 3 don't matter.
Yeah. So I think but this I think the more EA is actually this ADS3 picture actually where they take this k is equal to 1 limit where this you get this tensionless string. So there actually it is just these wrapped strings.
Yeah, then the bulk becomes the boundary.
Yeah, the bonds will become the boundary. And the point is that here
Long
also
strings.
actually, but here also actually it looks like it. Well, I mean, there is a in the tensionless limit. Actually, why can the string become very large even in asymptotically flat space?
Right.
Like the thing is that in ADS3, of course, you have long strings for any value of the tension, so that's not an EA. But if I go to an extreme limit, why can't I have a very long string?
Another way of saying it is if you have very high energy, you have the energy to make the string.
Yeah, I mean you don't need. I mean, of course, for finite tension we don't have it, but still I don't.
Just one comment. So along this line that W infinity is
Yeah.
the tensionless limit of on the ADS3 it is understood.
Well, the AD, yeah, I mean,
But
well,
when
no,
you
no,
go to
so
flat
actually,
space-
no, wait. So what they got is actually these W infinities, and these are the contractions of that. So these are the classical.
Yes, W1 plus N. But in flat space, it is the higher generalization of BMS3. So it
No.
is not exactly shown.
Well, the thing is that what turns out is that it is, well, the 4-dimensional asymptotically flat space that works like an ADS3. I mean, not like an ADS4. I mean, as far as the symmetry and these things are concerned. So that is the, in fact, the point is that 4 is the only dimension where a string worship can wrap the asymptotic sphere. Right?
This you are saying because the dual is CFT2, which is dual to
Well, I don't know. I mean, irrespective of any duality, I'm just saying, I mean, it's a geometric fact that it's 2 to match actually.
Sorry, I'm so ignorant, but just to say, for ages people have talked about the fact that at very high energies, string theory will have this huge set of symmetries which are then broken up. So no one can do a systematic analysis of the Veneziano, etc. amplitudes in that level and then cover the full symmetry.
You tell us actually what has been done.
I don't know the subject well enough, I'm asking. It's funny because Shiraz, sorry. Nobody has studied systematically the very high energy limit of Veneziano.
This is what I understood from this talk. The first person to do a systematic expansion of this was this thing. It's quite impressive.
Steve Waller, yes.
And cover the full symmetry group. No, is it too hard to do?
No, maybe nobody was looked. But I think this is the motivation. The motivation in that talk was...
Yeah, I mean, unless you have some motivation, you will not do that.
Well, for ages people have said, right, there's some huge enhancement, the full gauge symmetry of string theory.
Probably the people who say that people like Gross. Say all kinds of things so that you don't get serious. No, I mean, like you said, people keep saying and saying and saying and they don't know equation.
But this gross has they read some concrete thing, right?
Yeah,
all particles being massless.
That's what I thought.
Well, I mean,
that
some
limit,
massless.
No, they're very concrete.
The string field theory, they should
of
answer
all the
this question, right? I mean, they should know actually the answer to this question. I mean, if there is a A actually, I mean, this is string, I mean, people who do string field theory, I mean, they should answer this question.
No, absolutely. But even the fact that 2026 is the first time somebody has done a 1 by alpha prime expansion of Veneziano or 2025. That, I mean, if you're serious about this, you do things like this, right? It's not just something to put in your ground. I mean,
In Kanpur, they are doing this matching of Ross Mende and
Okay.
This
Yeah.
come
Who is this? Who is this?
Saddle point? Is it coming actually from?
Oh, they are doing this.
the way they did it was just they took
they
gamma
want to
functions.
just see whether this is the exact.
And then the hope is,
extreme height.
but that was not how it was.
Ross and Mende posed.
So the thing is that, yeah, so some higher spin algebra will be there. The string theory has higher spins. So, and in ADS3 algebra is not that intractable, that is not actually that having this kind of structure.
Well, it sounds really interesting to me. It sounds like, but one has to get formulas. Like this expansion in 1 by alpha prime.
Yeah.
If that, you take the leading term and
That
see this.
formula, of course, is not going to tell you what, well, I mean, that's very complicated to extract exactly.
Okay, but let's say that you claim that there is a higher spin symmetry, then you have to see how it acts on that formula.
No, that is known. I mean, we know actually.
Okay.
Yeah.
You know how all these symmetries are?
Yeah, I mean, that of course is known.
So then it is a symmetry.
So I mean, it is just H times G OP, that's what we know.
Okay, then the second question is, does imposing that symmetry determine that?
No, that will
So why should the corrections come out
But
of
that's
this?
a
No, that will be breaking.
Yeah,
That will be breaking.
See, I mean, that is a, well, that can in principle be done, but in practice, I mean, it is quite a difficult thing to do actually, to solve those PDEs and get.
No, I know. But just about Abhinit's question, what the hope would be that you see this infinite symmetry here,
Yeah.
and then you understand how that is spontaneous, somehow broken, and that determines the whole string amplitude.
And that should those corrections should also come out of that breaking.
Somehow, right? That would be like a Higgsing. That's what people used to say in the old days. That this symmetry is Higgsed. And that determines completely string theory. So the hope is that we understand how the symmetry acts on the leading term, then we understand somehow how Therefore, we get the first subleading term. Therefore, we get the second, and that the whole structure of string theory comes out of the symmetry. That would be totally fantastic.
Yeah. No, that will be fantastic. But well, I mean, yeah, implementing it is not.
Well, but just to say, I mean, in n equals 4.
Yeah, solving for the 4-point function is actually pretty hard. Actually, I mean, just imposing the symmetry. In fact, one master student in the view is just got the 3-point function. And we have not even done the 4-point function. Maybe the chat GPT can solve this. No, I mean, these are actually the things which I think this AI
might help.
Yeah.
But just to say, let's take n equals 4 and okay, at the free point, it's got this huge symmetry.
Yeah.
Now, sort of boundary conditions are breaking that symmetry because you're choosing the boundary condition of the dilaton to be not 0 but something small. So you go to interacting theory. So this would suggest that all of Yang-Mills theory, all of the amplitudes or all of the correlators are somehow determined by spontaneous symmetry breaking of the high spin algebra of the free theory. Those words have been around for a long time. Nobody's
but in the free super Young, I mean, that algebra is known.
At least some sub-algebra is known. It's high spin algebra. Okay, so that algebra, it's the algebra that Mother-Said algebra they've made a lot of use of. Very useful in some sense.
But that is for the 3 dimension, right?
Agreed. It's the same thing. So, but again, there's a jump between these words and doing something.
But this was in this Mallasana Zibodev, so that was, they also did this slightly broken higher
broken, that was really fantastic.
Yeah.
So now
but you are saying, I mean, no one has done that
corresponding
4 dimension.
For n equals 4. Right, there's a big difference between vector models and matrix models.
Yeah.
That's because every k-invariant operator in the vector model is one of the highest spin currents.
Yeah.
Or the sentence. So there the algebra terms everything sounds reasonable. In a matrix model, you've got these high spin currents. You've got many other things. Right? Just binding another high spin current.
But it can determine one sector of the theory. I mean, maybe not the full.
Maybe not the full thing.
Yeah.
But the hope might have been that you can reformulate n equals 4 Yang-Mills. You can compute the correlators of n equals 4 Yang-Mills by doing some spontaneous symmetry breaking or something like that of some known algebra. That would be really fantastic. And people said all these words. Like Bianchi, Weiser, all of those people. But nothing's happened.
Just a weak coupling, right?
So what was the stumbling block like? Why no one did this actually? I mean,
because in the end, if you try to take that to make it like equations, it's easier to actually solve Feynman diagrams than do this.
yeah, I mean there is no doubt about that actually. But I'm just saying, I mean, the fact that in principle, I mean, we can do this thing.
In principle, once you know the Lagrangian of the theory,
no, I mean, well, I mean, what I mean is that, I mean, that this works actually, not just.
Yeah, okay, I don't know. I would have to go back to those papers. But I'm just saying that 20 years ago, people said this a lot for Yang-Mills. There was a lot of words around and nothing happened. Nothing useful happened. I mean, it's not like people who want to compute anything. Not to be negative, I'm sorry. Just saying that there's a word to formula ratio that sometimes.
No, but these are all. I mean, there's no word here. I mean, so far, I mean, there's no.
No.
The thing is that now, I mean, as far as the string theory offers you, that's a different thing. But I think one could ask some basic question like, why? I mean, can one have a long string?
Yeah.
Even in arithmetically flat.
I would
flat space.
I think this is really interesting. But it would be particularly interesting if one could say something, as you said, about high energy string theory.
High energy string theory, yeah, I mean, that one has to. Well, I mean, that's not in. Yeah. That can be right. Yeah, great string theorists are in this room, so I mean, so.
Yeah, quite a bit of discussion.